All right, we're going to try to understand a simple second-order system that's exactly like the LRC circuits that we're studying in class. All right, this second-order system here is basically a pendulum, and it consists of a mass, some kind of a ball, that's located at the end of a string. Right now, in the picture I've shown right here, that ball is basically sitting lined up with the center axis. And we're going to say the ball is sitting at 0 degrees. That's the lowest possible point that ball can be at. Now, if I lift the ball up by pulling it back to, let's say, about 20 degrees from the axis. Now notice the ball was down somewhere low and I pulled it up a little bit higher. Remember from physics, if I pull something up, pull an object up a little bit, it gains some potential energy. Well, what's going to happen is if I were holding this here with my hand, then that ball has some potential energy in it. And as soon as I let that ball go, it's going to speed up. And that potential energy is converted to kinetic energy. Okay. Now, if it's the case that this little pivot point up here that this guy is connected to is really loose, in other words, there's not much friction there, this ball is basically going to go from having a lot of potential energy to a lot of kinetic energy, and then it's going to reach a stopping point on the other side. All right. Essentially, what's going to happen is I'm going to go from potential to kinetic to potential to kinetic to potential, and I'm going to go back and forth. And if there's no loss in this little pivot point, in other words, if the ball is able to pretty easily move around that pivot point, then what should happen is the angle of the ball should look sinusoidal as a function of time. All right, so let's watch this guy. I'm going to let him go. There you can see him moving back and forth. So he basically goes to 20 degrees, 0 degrees, negative 20, 0, 20. Essentially what's happening is I'm just converting the potential energy to kinetic energy and back and forth. So right now he's all potential, and I'm going to run it again. All right. If I look at the angle as a function of time, it looks like this. So essentially on the x-axis here, what I have is time. On the y-axis here, I have the angle. So I watch this guy, here's at 20 degrees, now negative 20, 20, negative 20, 20, negative 20. What's happening is the potential energy when he's at the height of his motion and not moving, all right, is at its maximum. And then at the bottom, he's got all kinetic energy. So essentially I'm just transferring energy from potential to kinetic and back and forth. And there's no loss in this system, so it just forever oscillates back and forth. Now we know that in reality that doesn't really happen. In other words, there has to be some loss in this particular pivot. And what happens is that means that some of the potential energy I start with initially doesn't get converted to kinetic energy. What's going to happen as a result of that? Well, if that happens, what it kind of means is, and you sort of know this, if I start out with this ball back at 20 degrees, let's take it all the way back there. If I start here at 20 degrees, what's going to happen is he'll make it all the way to the bottom and over here, but he's not going to make it all the way to negative 20. Maybe he'll make it to negative 19. And then when he swings back, maybe he'll only make it to 15 degrees. And eventually over time, he'll come to rest. So what we call that, all right, and the reason that happens, of course, is because of the fact that there's got to be some loss. In other words, some heat generated in this pivot. What we call that is damping. In this case, I can model that. I'm going to call it my damping. Let's set this guy and say there's a little bit of loss. Basically what I'm doing in my model is I'm saying that there's a little bit of loss in this pivot. So I'm going to let this guy run. And what I see is the ball swings a little bit less every time. In this case, what I see is the angle as a function of time, basically he doesn't swing as much, and so what I see is what I call a damped sinusoid. In other words, I see a sinusoid whose amplitude is decreasing a little bit. And the reason that amplitude is decreasing is because now there's a little bit of energy loss happening in this pivot. Well, what happens if that pivot got even tighter? Well, if that pivot got even tighter, let's say I did something like this. I can model the loss and say, okay, let's model that pivot a little bit tighter. All right, and I will. So I increase the loss in there. Now I let this guy run, and I see he overshot a little bit. Let me run that again. All right, so watch him. He overshoots a little bit and then comes back to 0. Here we can see the angle, right? So he started out a little bit more than 20 degrees, overshot a little bit, and eventually just kind of quickly comes back to 0. All right. What's happening again is I start out up here, I've got all potential energy, then I have a bunch of kinetic energy, but I'm losing the energy. All right, so eventually it just stops moving. All the potential energy I started out with initially is lost by the time I'm here. And if I get to the point where he's extremely tight, I can make him even a little bit tighter. What will happen is he'll just settle straight from being at 20 degrees initially and just go straight to 0 degrees. So let's try that scenario. So he just starts and sort of slowly moves into being at 0 degrees. All right. In that case, I show the angle like this. This would be what I would call an overdamped scenario. Okay.